So today we'll be looking at the DodecaPen accurate 60-year tracking of a passive stylus. This was done by investigated and applied by the Oculus research team, as you can see there. So we'll be looking first at the introduction to APRILTAGS, and then the 60UF DodecaPen. Then we'll go into some of the research concepts like calibration, APRILTAG detection, pose estimation, guessing extrinsics, the interframe corner tracking, dense alignment, the calibration for the DodecaPen itself, and the tracking. So in the paper, they had used Aruco markers, but this is also a project I'm currently implementing, and I use the April tags because they are more accurate and it works better at long range, and it's more flexible as well, and it's also less computationally intensive than the Uruka markers. And the April tags, they are a visual fiducial system, and they're used for augmented reality, robotics, and camera calibration, and it allows for the identification and 3D positioning of objects, and it acts like a barcode that stores information like the tag ID and position and whatnot. So yes, as you can see here, it allows for the accurate 6 degrees, so which is X, Y, Z, roll, pitch, and yaw, which is here as you can see in the GIF for the pose estimation. But there are some problems with this too, as the accuracy of the April tags for pose estimation is only good as the camera that's being used. Motion affects it, and the distance can also affect it. Of course, the longer the distance, the weaker the estimation, even though it's better than the Urco tags. So that is why finding the proper camera configuration parameters is very essential to to estimate any pose using April tags. So next we'll go into the system architecture diagram of what they had proposed in the paper. So what they had proposed is you have the camera here and you have the DodecaPen here, and you have the input frames. So what their system can do, it can track the 60 degrees of freedom pose of the calibrated DodecaPen here from a single camera with some millimeter accuracy. So you can see here that I'll show a video just now. They're drawing and it's tracing whatever they drawn into the computer. And what they did normal pose estimation at first, which is to detect the markers and to basically just get the pose by minimizing the reprojection errors. So I'll go into these later on. But this is just using a perspective endpoint algorithm to get the pose, and this is just the baseline. So if this did not succeed, then if the results weren't good enough, then we go into interframe corner tracking, which is where they use the pyramidal Lucas Canadian marker corner tracking, which is an algorithm which I'll also go into later on. And this is basically just decreases the appearance distance between each of the marker to be able to track it more efficiently. And then they go into getting the mask of they create mini maps of the DodecaPen here, and they normalized it. And then after doing that and getting to grayscale and whatnot, they would do dense alignment, dense pose refinement, which is just minimizing the appearance distance as well with Gauss, Newton, and backtrack inline search. And all of this is really just to make sure the tracking is as accurate as it can be. So I will show a little demo of what they have. So if you can see over here, so this is them drawing it on the paper and it's tracking it pretty accurately here. Yeah, that's it there. So it's pretty really accurate. So. And now we go into so now we'll go into how they actually did it. So the first thing is, of course, calibrating their camera. And this is using the pinhole model, which is basically used to get rid of distortion, like radial distortion, which has pin cushion and barrel distortion, as you can see in the images here, and tangential distortion. So during the camera calibration, you have a principal point in the middle of the image here, um, and this is the location of the optical center, and this is basically where all the lights hits the pinhole points, and you'd basically get the points in the image coordinate system that would respond to the world coordinate system, and the world coordinate system, that's the XYZ axis, which is the 3D world. And yes, and the camera coordinate system is basically just the camera and the XYZ of the camera, and well, the image coordinate system is just the image itself. And yeah, that's basically it there. And well, tangential distortion, this is what it looks like over here. So now we go into April tag detection, and this is just a library that was used over here, and it was just used. This was implemented in C, but there is a Python wrapper that I used that basically just to get the detections and the um, yeah, this to recognize the April tag and basically detect it on an object. And yeah, so it basically just computes the 3D position, the orientation, and the identity of the tags. And now we'll look at pose estimation. And before we go into the actual pose estimation, it's important to know the intrinsics and the extrinsics. So the intrinsics are basically in the camera world that I described before, and it describes how a point in that 3D world is mapped into the 2D image plane. And so these are the parameters that sit inside a camera, and it describes how, well, yeah, like what I just said. And it has about 4 or 5 parameters, which is basically just the camera constant, which is the distance of the image plane to the projection center in the image world. And you have the X and Y scale difference if the camera is being scaled. And then you have the camera focal length in the X and Y direction, and the principal point, which is the pixel in the image. And now, excuse me, now you have your extrinsics here, which describes where the camera is. So this is basically the XYZ location of where that camera is, and the 3D orientation of where that camera is looking at. And these three, so there's three, so these 6 parameters are basically the 6 degrees of freedom, or the 6-dimensional vector that we'll be talking about. And now we go into the perspective endpoint problem, which is basically the problem of estimating the pose of a calibrated camera when you're given a set of n 3D points in the world and their corresponding 2D projections. So basically, you're given the world points and the image points, and based on those points, you would basically find the pose based on that. So when you say find pose, you just basically find the rotation and the translation of the object as it's moving. And now we go into interframe corner tracking. So this is if it didn't detect the tags properly enough, then we implement this. So first of all, motion tracking is just recognizing the features and monitoring the motion across multiple frames. So example of this is like traffic estimation. And some of the challenges that these go through is that they would have rapid movement across the frames, motion blur, changing the object orientation, changing illumination, and interferent background. Or in this case, for the research paper, strongly tilted markers in relation to the camera. So this is if the like how it's in the dodecahedron shape, then there would be markers on the other side that you can't see and whatnot. So that would be strongly tilted. And the Lucas Kinect algorithm, this is the algorithm that the researchers use to implement the interframe corner tracking. So this is basically the where the motion of the features across the frame due to the relative motion between the scene and the camera are computed. And how they do this is by computing the image x and image y derivatives. So image x would be the previous image that's taken from the previous frame, and image y would be the current. And then you would find the difference between these two images. Then you would smoothen the image components and solve the linear equations for these, get the eigenvalues, and then you'd solve the equations with Kramer's rule based on the eigenvalues, and then plot the optical flow vectors that's returned. And in the research paper, they did the tracking in 2 rounds because they found that it still wasn't as accurate with just putting the algorithm once. So in the first round, they implemented it as normal. And so yeah, they got the pulse velocity and they tracked each of the detected markers. And then in the second round, they they rejected the markers where the pose velocity was more than 3 standard deviations away from the mean, and then they initialized the algorithm again with the trusted predictions from that first round. Before going this, I forgot that I had forgot to go through right for the pose estimation. I forgot to go through how they actually got the pose using self-PNP. This is an OpenCV function that basically takes the image points and the object points and the calibrated camera um, parameters and the distortions. And using that, they return the rotation and the translation vector. And you can also put in your own rotation and translation, like a predicted one, to even increase the accuracy of self PNP. And to project these points and or draw the actual pose onto the image to see it is just project points, which basically just take the object points as well and the pose that was returned from self PNP, and it just draws it into the 3D world. But it draws the 3D points into the image plane. And then you have to calculate the optical flow here. This is the OpenCV function that was used. Is basically take the, as I was explaining the previous and next image, and they take the window size and criteria, and it basically just returns the vector. And now we go into dense alignments. And this one, I didn't get to fully go into the maths for this one. So, but yes, but this is basically just to minimize the apparent distance between the image and the object pixels across all of the visible marker points. The method that they used to solve this was nonlinear least squares using Gaussian-Newton iteration. So the Gaussian-Newton iteration was used to approximate how the image changes with respect to the pose. And then to avoid anti-aliasing effects, they use this to ensure that the model markers are resampled as the same size as the image size, and they generated a minimap of the square markers to help with this. And as you can see over here in the system architecture diagram, this is the part that we talk about with the marker intensity, normalization, and dense pose refinement. So I'm not sure if you can see the mini maps there, but it's just basically a map of where all of the markers are. And the white and the black colors of the mask is just basically the active and the non-active regions. And now finally, we go into the DodecaPen calibration. So this was used to determine the precise pose of each of the marker with respect to the dodecahedron. And this is really important to get it to be accurate. As of course, if you don't, then it won't be able to track where it is. So this was used. You take several photos of the dodecahedron, and then you would basically get the pose, so the translation and the rotation vectors of each of the markers here in relation to each other. So for example, like maybe the top marker would just be 0 for the pose for translation rotation, and then the rest would just have the values corresponding next to how it is in respect to each other basically. And then the pen tip calibration is just basically to know the position of the pen tip for tracking. So again, they would just, when they have the pen inside here, they would just basically get that position of the pen in relation to the dodecahedron now. And then we go into the actual tracking, which is where they basically just use OpenCV or MATLAB or anything to actually trace what they are drawing. And that is basically where you have the puppy video that I had shown. And they even had like others, it's just Judy Bunny. So this is how this is it. This is basically just the tracking here, and this can be used for like many things like swarm robotics, so to uh just track an object or anything really, anything that involves tracking. So it's really good to use. And yeah, you can even use it in VR as well. Or if you want to, for example, guide a ducking boat to park somewhere, or even guide a vehicle to park somewhere, you just use that with the April tags. Oh, and of course, before I finish, the experiment results. This is it here. So this is over here is with the first one where you don't apply nothing. It's just the baseline pose estimation. So you can see how it's very shaky. And then you have it without dense alignments. This is just with interframe corner tracking. So it's a bit better. But then this is with the dense alignments with the nonlinear least squares algorithm. And yeah, it's a lot better here. And they also did an additional one where they captured it with motion cameras, about 16 of them. And this was, of course, the best one. But you can see it's pretty good with the proposed solution. So anybody could, do this at home if they would like to. And that is it for my presentation.
Yeah, thanks. Thanks, Gabby. Yeah,
Um,
I, I never knew about this stuff. I mean, you covered a lot of material
yeah.
in this short period. But are you planning to use any of this for something, or you just have an interest in it?
Oh yeah. Well, I'm actually working on this at Vertana right now. But I didn't share any information regarding that. It was shared according to the paper. But yeah.
Oh, Oh, I see. Okay. Vagina work.
Something similar to this. Yeah. So this is where the interest, and I thought it was really really cool how they did it, and that it's so simple. You can do it with stuff that you have at home. There's also libraries you can use to print your own April tags and just do it with the equipment you have.
Oh, you mean you could build your own
Uh,
pen and just use a standard
yeah, yeah,
camera?
yeah, yeah, yeah.
Oh, okay.
Once it is a bit tricky that I've only reached the dense alignment part, and it's quite a good bit of maths and whatnot. But yeah, they did it in a pretty simple way that anybody can do this if they want, which I really liked. Yeah. Well, besides the motion capture one, 'cause, yeah.
Yeah, I'm trying to think of a use case for it, to find, because it is interesting. But I
Yeah,
can't think of something to use it for right now.
but they had stuff like one of the use cases was um in ocean robotics where they used it to guide a a docking I guess it's a docking ship, a boat, yeah. Yeah, it's used to guide a robotic boat to park and to do certain things for them. So that is so things like that basically to track it. So I don't know
Okay.
if
All right, nice, thanks. No more
um,
questions for me. Yeah.
any more questions.
I got a question.
Okay.
Really like the presentation. I just seen in this picture here,
Mm-hmm.
there are multiple cameras, and I just wondering,
Yes.
like, how many cameras or angles you would need, for a good result.
Well, for this result here, the third one with their proposed solution, they only use a single camera for this. Um, but they also wanted to test it out with the 16 motion cameras. But in general, if you want a good result like this, um, it's just one camera. I'm currently using my webcam, and it's not really good quality, and it's going okay so far. But of course, the better quality camera, the better it would be.
Okay. So more cameras would just like make things more accurate, I guess. But just
Yeah, I'm not sure if you could see. I
make it
guess it's
finer and
sharper and
complicated.
more defined. Yeah,
Okay. All right.
but if you
Thanks.
want a pretty good result, just one should be enough.
And the pen, the number of sides, I don't know what, I forget what dodeca means,
Dodeca.
but how many
Oh,
sides does it have?
I think it's 10. Hold on.
10.
Yeah, I
Okay.
think so.
Yeah. So I assume that they found that to be, kind of optimal, right? I mean, because
Yes,
you could
12. 12.
potentially,
Sorry.
yeah,
Yeah.
12. Okay. Yeah. Because yeah, I guess it depends on the quality of the camera and the number of faces, etc. But
Yeah, yeah.
yeah.
I guess this could also be really good if for artists if they wanted to have a draw, I guess, and have their. I'm not sure. But yeah, it would be cool for visual artists, I guess.